Okay, it's good to be here, and thanks to the organizers for asking me to speak. The lectures I'm going to give are going to be, I imagine, different in flavor from the lectures from every other lecturer, in the sense that my mandate from the organizers, or at least the mandate as I understood it, was to give a set of introductory lectures on supersymmetric quantum field theories. My title says supersymmetric gauge theories, but you know, whether a theory is a gauge theory or not depends on the observer. It's not an invariant notion, so I'll broaden the mandate to supersymmetric quantum field theories. These lectures are going to be entirely introductory and will focus largely on symmetries, so that they can say, so that we can say as much as possible about large classes of theories. You know, so almost none of what I'm going to be talking about, again, as opposed to, I suppose, other lecturers, is my own work. Anyway, let's proceed. Okay, so these lectures are dedicated to supersymmetry, and in particular, supersymmetric quantum field theories. But to start with, maybe about half or a third of this lecture, what we're going to do is to follow a beautiful old paper by Witten, more than almost 40 years old now, and investigate for maybe half an hour, 40 minutes, one little supersymmetric model that is not a quantum field theory, that is just quantum mechanics. Okay, just so that we get all the ideas in place in a very simple setting, so that we can then fly faster later. Okay, so this is the model. So the model is a system of quantum mechanics of a particle in one dimension. Okay, so it's a non-relativistic particle moving in one dimension. The kind of particle you study about in Schiff's book on quantum mechanics. The one thing that's maybe not that puts you not in the first chapter of Schiff, but maybe the sixth chapter of Schiff, is that our particle is a has a two-component wave function. So its wave function psi of x is equal to phi1 of x, phi2 of x. It's the kind of wave function that Schiff would talk about if you were studying a particle with spin. Okay? So this is the system we're going to be studying. The Hilbert space is a space of square integrable wave functions, each component phi1 and phi2 square integrable on the real line, minus infinity to infinity. They're really very simple. Okay. Now, so we understand the Hilbert space, it's got the usual norm. Now the next thing I want to do to define the problem I'm going to be studying is to define the Hamiltonian wave. Okay? So the Hamiltonian we're studying will be defined by h is equal to x dot, since we're in Hamiltonian language, p squared plus w squared by 2 plus sigma 3 w prime by 2, I think by 2. Yeah, by 2. Okay, so we've got a particle, two-component particle moving in one dimension. We've got its Hilbert space, which is subject to this Hamiltonian. Okay, this looks like the kind of problem you could study about in Schiff. And, you know, it looks like it's nothing fancy at all. Why am I studying it for you? Why am I writing it down for you in these lectures on fancy topics? Okay, and the reason I'm doing that is that there's a hidden fanciness in this theory. And that hidden fanciness we see from the following considerations. Okay, consider the operator Q1 is equal to half sigma 1 p plus sigma 2 w, and Q2 is equal to half sigma 2p minus sigma 1w. I hope I got this right. Okay, These are obviously operators acting on the Hilbert space of our system. P is the usual operator, right? So P is equal to minus I del x. Sorry, thank you. And here W is a function of x. Okay, so P is the usual operator on wave functions of Hilbert space. W is just multiplicative operator in the x basis, the usual kind of thing that we study all the time in Shift. Okay, now in order to proceed with the analysis of this theory, sometimes convenient to define Q plus, which is Q1 plus IQ2, and Q minus, which is Q1 minus IQ2. Okay? If we make the definition sigma plus is equal to sigma 1 plus I sigma 2, and sigma minus is equal to sigma 1 minus I sigma 2, and if I have not messed up, 2 minutes of algebra will show you that this is sigma plus by 2, P minus IW, whereas this is equal to sigma minus by 2, P plus IW. Okay. All you have to do is to, so for instance, this is obvious, right? Sigma 1 plus I sigma 2 into P, and sigma 1 and minus I sigma 2 into P, and you have to pull out an I for the other term. Okay? Now, why am I interested in these operators? I'm interested in these operators because they obey a certain interesting sort of quote-unquote algebra. And in order to see that, let's just work this out honestly. So suppose we have Q plus, Q minus. I'm just going to evaluate Q plus, Q minus. Okay? So Q plus on this 2 cross 2 space, this is simply sigma plus, sigma minus by 4. And then we have P minus minus IW, sorry, P minus IW into P plus IW. Right? Because the differential operators have nothing to do with the 2 cross 2 space. Multiplication by x, so differential operators have nothing to do with the 2 cross 2 space. So they just go through each other. Okay? So that's Q plus times Q minus. What about Q minus times Q plus? Okay? This is sigma minus sigma plus by 4 in a P plus IW into P minus IW. Okay? So what? Now, let's look at the anti-commutator. Q plus, Q minus, which by definition is Q plus, Q minus Q minus, Q plus. Okay? Let's look at this anti-commutator. Well, all we have to do is add these two. So let's see. There are some terms that appear here with the same sign. These terms are the terms which I get by taking P square and the W square. Okay? So you see that what we will get is sigma plus sigma minus plus sigma minus sigma plus by 4 in a P squared plus W squared. Okay? And then there are the terms which occur with the opposite sign. So those are the terms that occur with the those are the terms that sort of like are the cross terms, and well, let's work those out. Those would be minus I times WP plus I WP. Okay, so we can write it as plus I times PW into sigma plus sigma minus minus sigma minus sigma plus. Divided by 4. Is this clear? Yes. W is any function of x. We'll see. You see from the Hamiltonian here, that W square is the potential. Okay, so it's sort of like the square root of the potential. Exactly. So for instance, if W was a linear function, this would have the potential of a harmonic oscillator. Okay, but right, excellent. So W should be thought of as roughly the square root of this potential here. Okay, but we know what sigma plus and sigma minus are. Okay, so we can just evaluate the anti-commutator of sigma plus and sigma minus, and the commutator of sigma plus and sigma minus. Okay, the anti-commutator of sigma plus and sigma minus, let's see. So you get a sigma, you get, this is basically 4 times identity. Okay, so this gives us p squared plus w squared. On the other hand, this guy gives us plus sigma plus sigma minus sigma x. Okay, yeah. So this guy, I think, gives us plus sigma z. So plus I times sigma z in a p. Yeah, right. W. Yeah, so sigma 1 and sigma 2 are the usual sigmas, right? So sigma 1 times sigma 2 is I times sigma 3, and therefore commutator will have a factor of 2. So it's the usual Pauli matrices. Okay? Now we use the fact that P commutator W, okay, is minus I del by del x of W. The minus I cancels this, and so this is simply equal to 2h. Where h was the Hamiltonian we defined before. Because W prime was the derivative of W with respect to x. Is this clear? So what we found is a marvelous result. We found that the Hamiltonian thank you. We found that the Hamiltonian of our problem is sort of the square of something more elementary. And actually we can see this the squaring business a little more clearly as follows. Suppose we worked out the algebra not for q plus and q minus, or just substituted back what q plus and q minus were in terms of q1 and q2 in various ways. You can show that q1 square, okay, qi, qj, going back to q1 and q2, is equal to delta ij times h. Okay, similar algebra. So in particular, q1 squared is equal to h, q2 squared is equal to h, but q1 q2 plus q2 q1 is equal to 0. Okay, so in this language you see it even more clearly. The Hamiltonian is a square of two objects. It's q1 squared, same as q2 squared. By the way, you can easily check, I haven't mentioned this, but it's easy to see, that q1 and q2 are Hermitian operators. Right? They're Hermitian operators because p and x are Hermitian, and sigma 1 and sigma 2 are Hermitian. Okay, and therefore, yes, please. Yes. Yes. No, yes. 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 It's delta ij, so the right-hand side is 0. Excellent. What? No, not 2 delta ij, delta ij. You see, this plus minus is neither 1 nor 2. This 2, you see, Q plus is Q1 plus IQ2. Q minus is Q1 minus IQ2. So it gets contribution from Q1 squared and Q2 squared. So it's a negative factor of 2 here compared to the factor here. So this is really delta H. Yes. Louder, a little louder, please. Anti-commutator, yes. Oh, 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 oh. Yeah. No. Oh, you're right. You're right. You're right. Thank you. Thank you. 2Q. Thank you. Thank you. That's it. That was the question. I'm sorry. I'm sorry. Right. This was right in terms of commutators. It was wrong when I wrote the squares. Sorry about that. Thank you. Okay, excellent. Now, why is this important? You see, important or not is certainly interesting. It's interesting because the Hamiltonian is the square of another operator. And it's sort of also interesting because, because you see that what's happening here is that you've got three operators in the game, three Hermitian operators in the game, Q1, Q2, and H. And they obey a sort of Lie algebra between themselves. We've already seen that Q1 anti-commutator with Q1 is H up to some factor of 2. Q2 anti-commutator with Q2 is also H up to a factor of 2. Q1 anti-commutator with Q2 is equal to 0. Now, so there are three things participating, Q1, Q2, and H. And you can ask, what about, for instance, Q1? I'm going to take the commutator. We'll figure out the rule in a minute. I'm going to take the commutator of, let's say, Q1 with H. You can ask, what is that? But this is very easy, because H is Q1 square, up to a factor of 2. And therefore, Q1 anti-commutator with H is 0. Okay. So this is equal to 0. So you see, this is something like what you get when you have a Lie algebra. When you have a Lie algebra, you have commutators of various generators being linear combinations of other generators. Here what we've got is something like that, but not quite that. We've got two kinds of operators. Let's call Q1 and Q2 the fermionic operators. We'll see why in a moment we call them fermionic. Okay? Let's call H the bosonic operator, the bosonic generator. And what we're seeing is that there's a new rule. The rule is that if you take the anti-commutator of the fermions with themselves, but the commutator of, if you've got a boson and a fermion, or as we will see later, boson and boson. Okay. If you've got two fermionic generators, you take the anti-commutator. Or on the other hand, if you've got either one bosonic or two bosonic generators, you take the commutator. In this simple setup, what we see is that the right-hand side is a linear combination of other generators of the algebra. Okay? So this feels a little bit like it's generalizing the usual notion of continuous symmetries. Okay? The usual notion of continuous symmetries is based on Lie algebras. Lie algebras have commutators with these generators being linear combinations of other generators. We've got something very similar here. Except that sometimes we use, we grade the algebra. We break up the generators into fermionic and bosonic generators. And then we look at either commutators or anti-commutators, depending on which ones. This we see in front of our eyes. Okay? Now, there are two or three things that I want to understand about this theory, partly for fun and partly because we will come back to them maybe in lecture 3. Okay? Before we go on to generalize this theory to more quantum field theoretic kind of theories. Okay, so the things I want to understand about this theory are the following. Firstly, what is the consequence that of Q1 squared being equal to H? Remember that Q1 is a self-adjoint operator. Okay, so Q1 squared is the same thing as Q1 dagger or Q1 dagger Q1, and therefore it's a positive definite operator. Okay, so this tells you immediately that in this theory, H is positive definite. By which I mean that the action of H on any given state, let's say the expectation value H, or every eigenvalue of H, is positive or 0. That's obvious. Okay? It's not entirely obvious when you look at this. You've got the sigma 3 that has eigenvalues plus minus 1. It's not entirely obvious, but once you think of it this way, H is clearly a positive definite operator. Therefore, given any eigenstate psi, such that H psi is equal to E psi, we have E is greater than or equal to 0. Now, whenever you have a situation where you have an inequality, it's always interesting to consider things that saturate it. In this context, it's even more natural because H is not just some garden variety operator, it's the Hamiltonian. And states that saturate this inequality are states of minimum eigenvalue of the Hamiltonian, that is minimum energy, namely the vacuum. As everyone knows, the vacuum is a very special state in any quantum system. Okay, so it's interesting for 2 minutes to consider what the vacuum of this theory looks like. Okay, so we're going to study states such that H of psi is equal to 0. The question we're going to ask is, do there exist such states? Can we find them? How many of them? Okay? Now, H of psi is equal to 0 is some equation. Okay? However, if we look at this, remembering that H is Q1 times is Q1 squared, this is the same as Q1 on psi is equal to 0. These are equivalent statements. How do you know they're equivalent? Well, clearly, if Q1 on psi is 0, that implies H equals 0, because then Q1 squared on psi is 0. On the other hand, suppose H on psi is equal to 0. So this is a little box. Suppose H on psi is equal to 0, then that implies Q1 squared on psi is equal to 0, which implies that psi Q1 squared psi is equal to 0, which implies that psi Q1 dagger Q1 psi is equal to 0, which implies that Q1 psi is equal to 0, which implies that Q1 psi is equal to 0. These standard manipulations, right? You've got if H and psi vanishes, then that tells you that Q1 psi has 0 norm. The only state with 0 norm is the 0 state. Therefore, Q1 psi is 0. Okay? That's great. So, at the level of differential equations, we get a payoff in trying to solve Schrodinger's equation at 0 energy. Instead of having to solve a second-order equation, which we would normally have to do here, we get to solve a first-order differential equation. Okay? Now, first-order linear differential equations are always very easy to solve. In this case, we're just going to go ahead and solve them. Okay? So let's see. So what we have is Q1 was proportional to sigma 1 P plus sigma 2 W. Yes? What? It's difficult to see there. Clearly ICTS should have built bigger blackboards. Okay. Yes? But I think the angle is so that is that right? What about the people in front? You see, I think this is the worst angle. Do the people in front want to just move up a little? Okay, so I'll just stop. And anyone who can't see, please let me know. It's easy, I can see the equations. Okay, so Q1 was proportional to sigma 1, and this is minus I del by del x, plus sigma 2 W. So that's proportional to sigma 1 into minus I del by del x. And now we want to get sigma 2. So that's sigma 1 times minus I sigma 3, I believe. Right, because sigma 1, sigma 3 is I sigma. No. Plus I. Sigma 1, sigma 3 is minus I sigma 2. And so that does it. Right. Okay, great. So if Q1 annihilates the state, so does this quantity, because sigma 1 has eigenvalues plus minus 1. So the only way that this can annihilate the state is that this whole thing annihilates, the guy on the right annihilates the state. Okay, and so we get the differential equation minus I del by del x plus I sigma, so we can cancel the i's, put a relative minus sign, sigma 3w on psi is equal to 0. Okay, and that tells you that psi is equal to exponential of integral of sigma 3 can go out, w of x dx, acting on any column C1, C2, where C1 and C2 are just constant numbers. Is this clear? Okay, so immediately we've seen that that if there is a ground state, in this problem, this ground state is unique, right? Because we just solved. Oh, well, it's unique. Sorry, it has the at most two ground states because the C1 and C2. This looks like a Dirac equation because it's first order. Yeah, supersymmetric states often, instead of being second order differential equations, be first order. That's the reason it's looking like a Dirac. Great. Any other questions on it? Okay, so we've immediately seen here that we can just solve for the ground state. However, the next question is, are these all legitimate states in the Hilbert space? So when can a wave function not be a legitimate state in the Hilbert space? Anyone? Loudly. Not square integrable. Excellent. Okay. It's a very important part of quantum mechanics that isn't enough emphasized sometimes. If you allowed states that were not square integrable, then the harmonic oscillator, you would have states that were annihilated not by A, but by A dagger. And those states, by the formula for the Hamiltonian of the harmonic oscillator, would have energy not plus omega by 2, but minus omega by 2. And then you could keep going, and you'd have an unbounded spectrum from below. Yes. So the fact that things are square integrable is a crucial part of quantum mechanics. You give it up, you get nonsense. Okay? So, there's a story about this, but I'll tell you guys later in the discussion section. It involves loop quantum gravity. Okay. Okay. Fine. So let's keep going. So now, suppose I'm going to restrict attention to functions W. So far could have been anything to W's that go so that at plus minus infinity, the potential rises. So W squared increases. I don't really care how fast as we go to plus minus infinity. Okay? Since W squared must increase as we go to plus minus infinity, W must either increase or decrease. Either go to plus infinity or minus infinity as we go to plus minus infinity. So we have two options. We can do all kinds of zigzag, but either W should go like this, or W should do this. These are the two possibilities for W subject to my restriction that W squared increases at infinity. Okay. Now let's see. Suppose we had W doing this. Then this integral would be of opposite signs and plus and minus infinity. Can you see that? Suppose you've got for instance, suppose you had just some function that was positive everywhere. If you go to plus infinity, that integral is positive, but if you go to minus infinity, that integral is negative. For instance, a constant. Okay? And now you see the problem. You see that there are various kinds of things we can fool around with the eigenvalue of the sigma 3. But if you've got things going to opposite signs at plus and minus infinity, you've got a relative problem. And there's no way you can fix that. So either at plus infinity or at minus infinity, this wave function is going to be not square integral. Is this clear? Okay? So if you've got a potential of this sort, we conclude no supersymmetric states. No states with h equals 0. Is this clear? Can I repeat? Okay. Let's look at this integral wx as a function of x. Okay? Okay, so forget about the sigma 3 for a moment. Just let's look at the integral wx as a function of x. Suppose w was a function like this. Then, clearly, as x goes to infinity, the integral of wx is positive. Whereas as x goes to minus infinity, the integral of wx is negative. Can you see that? Because it's the integral is an always increasing function. So when a function increases as you go towards positive x, it decreases as you go towards negative x. For instance, if x was x squared, the integral would be x cubed, which grows to positive infinity and decreases to negative infinity. Is this clear? Okay? So if a function looked like this, then it goes to either, let's say it goes to, it depends on signs, but it's fine. So if a function looks like this, it goes to plus infinity as x goes to infinity, but goes to minus infinity as x goes to minus infinity. No state. It's not just bound. You see, now this sigma 3 here is an operator whose eigenvalue is either plus 1 or minus 1. So we have two options. Either we choose eigenvalue plus 1 or we choose eigenvalue minus 1. If we choose plus 1, then our wave function is not square integrable at infinity, because it grows there. If we choose minus 1, our wave function is not square integrable at minus infinity, because it grows there. I'm implicitly assuming that this growth is faster than a certain... Yeah, well, it's a growth, that's enough. It's not square integrable. Is this clear? Now, there are two other possibilities, okay? The flips of these two. But you see, it's the same thing, right? If I flipped this, I will change which end is not square integrable, but it won't change the fact that if it's the flip of this is also not giving rise to a square integrable wave function. Is this clear? On the other hand, let's look at this. Here, this function increases as we go to infinity, but also increases as we go to minus infinity. The integral of that function. Is this clear? It's like x. X integral is x squared. Increases both ways. Okay? So if we had a function like this, if we choose this as yet unknown eigenvector to be a vector whose eigenvalue is minus 1 under sigma 3, okay, then this function is square integrable both at plus and minus infinity. Okay? Had I got the flip, I would have chosen the function whose eigenvalue under sigma 3 was plus 1. Would have been square integrable under, as we went to infinity. In both cases, what we have is that there is exactly one ground state, exactly one supersymmetric state. So in this case, we have one SUSY state with E equals 0. Is this clear? No, we don't care about convergence. You see, we're not evaluating this function at infinity. What we're doing is evaluating e to the power of the function at infinity. So if that, e to the power minus infinity is perfectly well behaved. So we don't care about, it's not a problem if the function goes to infinity at infinity. Okay? We just need to be able to evaluate this integral. So for instance, think of this as being x. Then this is x squared. The wave function is e to the power minus x squared. We have the harmonic oscillator. There's no problem. Is this clear? Which flavor of that graph?
The flip.
The flip would be another problem. You see, W is not part of the state, it's part of the problem. The logic is I give you W and then you solve my problem. Okay? So there are two classes of Ws. One class which admits a supersymmetric ground state, the other class which does not. Is this clear? Okay? Yes? How did you get one supersymmetric state in the first class? You see, when we look at the integral of W As we go to infinity, it becomes, maybe I should write this down. Let's look at this. Yeah. Integral w of x as x goes to infinity is equal to infinity. Okay? Integral w of x as x goes to minus infinity is also equal to infinity. Positive and very large. And therefore, we have this integral w of, therefore, now suppose we choose this. So then we take psi of x is equal to exponential integral w of x sigma 3 acting on 0, 1. But sigma 3 acting on 0, 1 is minus 1, which is equal to exponential of minus integral w of x. This is the exponential of minus a function that grows both to positive as well as negative infinity. And therefore, the function that decays both large x, positive and negative, and therefore square integrable. At least if it decays fast enough, I'm assuming. Yeah. What? Is a key factor, absolutely. Absolutely. If I integrate over wave, yes. So you're pointing out that I'm being very sloppy in my notation. I'll be less sloppy. As we go on, my sloppiness will increase, I warn you. What I mean by this is the following. Integral some number, let's call it 0, it doesn't matter what, 2x w of y dy. That's what I meant when I sloppily wrote it. Okay, it's a sense in which integral of x is x squared by 2. That's what I meant. Yeah. The question is, what happens if wx remains bounded at plus minus infinity? This is a more delicate situation, which I don't want to consider. I want to be in a situation where we're looking at discrete, where my problem has discrete eigenstates. Okay, that requires a potential to go like this. When the function remains bounded, then we have to discuss how it goes to that bounded value. Okay, and that's a more delicate discussion I don't want to get into right now. We could do it. It's an interesting question. Okay, then you have scattering states, potentially, and so on. Okay, let's avoid that for now. Yes? Are not both square integrable. That's why, in this case, we have exactly one supersymmetric state. If both were, we would have had 2. In this case, we have 0. Is this clear? It's an excellent question. The question is the state bosonic or fermionic? We're going to answer this. We're going to answer this in the next 5 minutes, 5 or 10 minutes. But before we do that, we are going to have to define when a state is bosonic and when it's fermionic. So we're going to answer this, but hang on for 2 minutes. It's an excellent question. Okay, now let's keep going. The next thing I'm going to do in this very simple model is to ask whether I could understand this interesting property. This interesting property of number of ground states, number of vacuum states of the problem, number of zero energy vacuum states of the problem, semi-classically. Okay? So semi-classically, can I understand, can I compute how many ground states are on this problem? Now what does semi-classical mean? Semi-classical means we've got a small h bar. So the particle doesn't fluctuate very far from any minimum in the potential. That's what semi-classical means. Now our potential was w squared. So ground states like to sit near where w is equal to 0. So let's suppose we have this problem. we have many points where W is equal to 0, 5 in this problem. Okay? Semi-classically, it looks like, classically, it looks like we've got 5 ground states. Now, what was semi-classically? What does semi mean? It means taking into account the first quantum effect. That's what it should mean. People often say semi-classically when they mean classically. But here we're going to actually mean semi-classically. Okay? So let's look at the Hamiltonian. H is equal to p squared by 2 plus w squared by 2 plus sigma 3 by 2 w prime, sigma 3 by 2 w prime. That's, yes? Yes, we should expect the particle to sit at the minimum of the potential. But that's not the same as the minimum of W. Because V is W squared. Notice that if V is W squared, the minimum of V is 0. Because nothing squared is less than 0. As long as it cuts 0. Okay. Clearly, if this W never cuts 0, then even classically there are no ground states. Hard to believe that quantum mechanically there will be. Certainly semi-classically there will not be. Okay, so if W never cuts 0, we're in good shape. If W never cuts 0, we're in this situation. Because how can this potential never cut 0 and rise on both ends? It has to rise with the same sign. Okay, so this quantum answer that tells us that we have no ground states, if W never cuts 0, it's obvious classically. Okay, what's more subtle is when W cuts 0 at a few points. Okay, so let's take one of these points. Let's say that this point is x star, and we want to understand this Hamiltonian, the spectrum of our theory, the lowest energy state of the theory, for the states localized near x star. So suppose W never cuts 0. Then let's draw a graph of something that never cuts 0 and goes to either plus infinity or minus infinity at both ends. It could do this, or it could do this. In either case, we're in this situation. And therefore is the situation where we concluded quantum mechanically there were no A equals 0 ground states. Now, this is an obvious statement classically. Because there's no configuration classically in which W squared is equal to 0. So the Hamiltonian never vanished. That's what I mean. That's what I mean. I mean a supersymmetric ground state, sometimes. Right? What's more subtle is when semi-classically, or well, classically, there are ground states. When W cuts 0 somewhere. That's more subtle. Is this clear? Okay. So suppose it cuts 0 at the value x star. Now, since we're being semi-classical, we don't explore the potential very far away from W. Just explore it as H is equal to p squared by 2 plus W prime at x star. X minus x star, the whole thing squared by 2. Semi-classically, that's the potential we see. And we also see plus sigma 3 by 2 W prime at x star. Actually, in this case, we don't need to expand further, because that's non-zero, and if you look carefully, there's an h bar here. I've omitted all h bars. So it's just the leading order is what matters. Now, this problem all of us know how to solve. See, we're regressing. We're going from quantum mechanics in one dimension to the harmonic oscillator in one dimension. Okay. This is a problem all of us know how to solve. We all know that omega is square root of k by m. M is 1 in this case. K is this W prime. So omega is equal to W prime of x star mod Thank you. Thank you. No square root because of the error that was corrected. Okay. And therefore, the energy of this bosonic part, so E min, is equal to this by 2, h bar omega by 2. But let's look at the energy of this part. Sigma 3's eigenvalue is plus minus 1. So this is plus minus W prime x star by 2. And now we see a marvelous result. The result is that if we choose the minus sign, this cancels this. Oh, sorry, if we choose one of the two signs. If this is positive, we choose the minus sign. If it's negative, we choose the other sign. Yes? There is, but that will be subleading. You see, the particle sees whatever it sees most easily. That will be higher order in h bar. That was my comment. I hadn't kept track of order h bar here. But if I did, you'd find that there's an h bar here. So this automatically is order h bar. Fluctuations in the wave functions are also order h bar. So higher order terms will be order h bar square. Okay? I'm being semi-classical, which means I'm giving the first quantum correction, not the second quantum correction. That's a harder calculation. Okay? Excellent. So now you see that we can always choose one of these two signs so that we get 0. Semi-classically, therefore, we found that every time this W cuts the axis, we get a 0 eigenstate. So if you had this problem, and you asked yourself, semi-classically, how many zero energy eigenstates are there? You would get the answer 5. Okay? Quantum mechanically, we've seen that the answer is 1. I won't really go through the... Okay. Yeah. The last step. This part, here. Okay. You see, what we've got here is a Hamiltonian, which is the sum of two decoupled Hamiltonians. A Hamiltonian for the x motion and the Hamiltonian for the spin motion. The Hamiltonian for the spin motion is decoupled from the x motion because this is a constant. Okay? So we can compute these two Hamiltonians compute with each other. So the eigenvalues are just the eigenvalues of each Hamiltonian added up. Okay? The eigenvalue for this Hamiltonian is the lowest eigenvalue, is the ground state of the harmonic oscillator, which we computed to be thus. These eigenvalues are just those of sigma 3. Is this clear? Okay? What we're seeing is that semi-classically, every time W crosses one of these axes, we find a 0 energy state. Now, what do you suppose I went not to order h bar, but to order h bar to the 10? Does anyone have any guesses? With these 5 states, we know exactly those 5 states become 1 state. At h bar to the 10, do you have a guess? Would it, if we to what order in h bar would we have to go to see this? Any guesses? Any reasons? That's the number of orders on h bar we have to go. It's a good guess, but I see where you're going, but no, not right. That's another good guess. But you know, in a lecture course, when somebody asks you an answer, it's a good guess the answer is either 0 or infinity. Because nobody expects you to calculate on your feet. Can't be 0 here, so by QED, it must be infinity. Okay? And no order in the h bar expansion. Will this ever be lifted? How do you see that? You see that because orders in the h bar expansion depend on the function in the neighborhood of a point. But the question of whether you've got a node here, I've not said anything about analyticity. The question of whether you've got a node far away is totally independent of the expansion on this point. See, I can take two functions, one of which does this, and then goes up here. The other of which does this, exactly the same, and then goes down here. One of them exactly has an eigenstate, the other one does not. That clearly cannot be seen by looking at the expansion around that point. It's got to do some global features of the problem. Okay. So it must be non-perturbative in h bar. Must see tunneling effects. This is the right answer. Okay? Excellent. So we've already seen something sort of interesting. It would be possible to construct instant-on solutions, and people have worked this all out to death. But we don't even need to. We see, because we're reading Witten's papers, you never need to do a calculation. it's just the answers so clear. Okay, great. Now, let's keep going. Now I want to try to, I know we want to move on. I'll take 10 more minutes on this model and then just move on. But I want to try to address Indranil's question. Indranil wanted to know whether the ground states were fermionic or bosonic. Stability, it's very stable. I mean, what do you mean by it? Are you worrying about decaying? The Hamiltonian is bounded from below. That's a totally stable system. Okay. W squared is completely stable potential. There's no issue of stability. But there's an issue of stability of your calculation. The calculation is how stable is an approximation that tells you have found 5 ground states. That, as we've seen, can be very unstable. Okay. 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 Now, what I want to do is very quickly, maybe I won't go through all the algebra here. I'll show it to you and ask you to verify some of it. Just so that we get past quantum mechanics in this lecture course. Okay. 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 Let's see. So, in order to address Indranil's question, of course I could just make some definitions, but in order to address it in a way that you will find satisfactory, in a way that will generalize to higher dimension, the interesting thing is to do is to take this model and view it from the point of view of a Lagrangian. You know, in quantum mechanics, we're very used to following Schiff, writing down Hamiltonians, and then we proceed. In quantum field theory, we usually don't write down Hamiltonians, we write down Lagrangians. Okay? So the question I'm going to ask, the question about Lagrangian is sort of interesting. It's a question of what setup do you write down whose quantization produces your Hilbert space and produces this Hamiltonian. And now the only subtle thing is that we have to produce this two-state system. It's quite hard classically to produce two-state systems. I mean, you know, to write down some phase space that produces two-state systems, possible. Possible. But you know, the thing that we're going to do is to write down a Lagrangian which includes anti-commuting variables. Because quantization of Lagrangians with anti-commuting variables very easily produce two-state systems. Okay? So the Lagrangian we're going to write down is here. And now here, I tried to work out all signs last night, but I won't swear I got them all right. Okay. L is equal to x dot squared by 2 minus w squared by 2 plus I psi dot, or maybe minus I. This is the sign I'm least confident of. Psi star dot minus psi star dot psi by 2 minus psi star w prime. Okay. That's no sigma 3 because there is no two-state system anymore. Okay. Now, so let's see, what are we doing? What we've got is a Lagrangian that is function of the bosonic coordinate x and the fermionic coordinate psi and its complex conjugate psi star. Psi and psi star, two different fermionic coordinates, which we can think of as complex conjugates. Okay? Now, by fermionic coordinate, I mean what I hope all of you know. It's an something that obeys this anti-commutative, this algebra, right? Theta 1, theta 2 is minus theta 2, theta 1. Theta 1 squared is 0, and so on. You all know this. I'm not going to review that for you. Yes? Where the dots are. This is the part I'm least comfortable about, but you see, it's either this. Where have I put it? Plus. Give me a minute. The relative sign I can figure out. If we integrate by parts plus, yeah, so this is a plus relative. Right? Because if you integrate this guy by parts, you will shift this here with a minus sign and then flip them through, there's another minus sign. So the relative sign is a plus. I hope this overall minus sign is correct. If not, you guys are so good at algebra, you'll correct me, right? You'll tell me. Okay. Fine. So now, what we have here is a Lagrangian where the basic degrees of freedom are a bosonic variable x and a fermionic variable psi. And if we go through and quantize this system, in the way that you are supposed to quantize fermionic theories. You will find psi star anti-commutator is equal to 1. Okay. Now X has its usual algebra, right? The momentum is X dot. X commutator P is 1, so Poisson bracket P is 1, so X commutator P is I. That's the usual story. What's unusual is this fermionic business. Psi star anti-commutator is equal to 1, and this is implemented by the algebra. This is implemented on a two-state system, where psi is equal to sigma plus by 2, and psi star is equal to sigma minus by 2. So that's a very nice way of producing a two-state system. You just introduce two fermionic coordinates, put a sort of standard kinetic term. The quantization of that theory produces the two-state system. And it produces it in this way, that it turns psi into the operator sigma plus by 2, and psi star into the operator sigma minus by 2.
Quantum level, right? This is sort of Lagrange.
This anti-commutator is at the quantum level, correct. This is quantum statement of operators. It's really the statement that these operators obey this relationship. We want to quantize the system is to look for operators that obey this algebra. Okay? Excellent. So let's keep going. So now we can work out what psi star is. And again, if I've got my signs right, once you substitute psi is equal to sigma plus by 2 and psi star is equal to sigma minus by 2, you will get minus sigma 3 w prime. Minus because Lagrangian has minus of potential. Okay? So this Lagrangian is just a rewriting of the Hamiltonian we started out with before. But it's a rewriting in a Lagrangian form, and it's a rewriting that involves fermions and bosons. Okay? Now, what do we mean by fermion number? What do we mean by fermion number? By fermion number, okay, that's essentially arbitrary, but difference between fermion numbers is not arbitrary. So let's make a definition. Let's say that this state, with this choice of quantization, let's say that this state, 0, 1, has f is equal to 0. And this state, 1, 0, has f is equal to 1. Why is this a good definition? It's because 1, 0 is, let's say, psi star, or is it psi? Psi is psi on 0, 1. Psi is the object, which is the fermionic operator. So 1, 0 and 0, 1 should differ by fermionic number 1. Okay? So this is an assignment that gives my psi fermion number 1 and psi star fermion number minus 1. Okay? So state which is like 1, 0 has fermion number 1 and 0, 1 has fermion number minus 1. Is this clear? Now we can address Indraneel's question. Because you see, we discovered that the sign of this sigma 3 was completely fixed by what W was doing at infinity. Okay? So if W was increasing at plus infinity, if W was like this, then we had to choose the wave function 0, 1. And in this case, the quantum mechanics state. Okay? The quantum mechanical state, the unique round state, had fermion number plus 1 with my conventions. Sorry, 0. 0 with my conventions. Thank you. Okay? On the other hand, if you looked at either this calculation, you see, once again here, what you're seeing is whether we choose plus or minus. That's the question of whether we're choosing 1, 0, 0, 1. That depends on the sign of W prime. So what we're seeing is that the rule is that exactly quantum mechanically in the case that for the one state, or semi-classically for each state, if For W's that cut the axis like this, fermion number is 0. For W's that cut the axis like this, fermion number is 1. Okay? And so what we're seeing is that in this problem, we had 3 states of fermion number 0 and 2 states of fermion number 1. Now, what's often more interesting than fermion number is the quantity minus 1 to the power f. Okay? What's often more interesting than fermion number is the quantity minus 1 to the power f. And what we're seeing is that minus 1 to the power f is equal to 1 for 3 states and is equal to 0 for 2 states. As in minus 1. Minus 1 for 2 states. In this problem here. Okay? Is this clear? So semi-classically, we got the number of ground states very badly wrong. But yes? Can I assign assignments 0, 1 to this slope? In fact, I assigned to this, I assigned 0, 1, and to this I assigned 1, 0. Why is that? Okay. Let me look at my, You see, this guy is always positive. So what we want from here is the negative value. If this is positive, and we want the positive value if this is negative. Is this clear? Okay? So let's take the case where this is positive. Then we want the negative value for sigma 3, but the eigenvector with negative value for sigma 3 is 0, 1. Okay? So when we're going like this, we should choose the eigenvector 0, 1. Is this clear? On the other hand, when it's like this is already negative, so we want the positive eigenvector from sigma 3, and so we must choose the eigenvector 1, 0. Is this clear? So that's the rule. Clear, everyone? So what we've seen is something else quite interesting. What we've seen is that in this problem, yes? This is an arbitrary choice. Let me say that in my Lagrangian, I wanted this operator psi to have fermion number +1 and psi star to have -1. Okay? Now, what number I associate to the ground state is not important. What's important is the difference between the fermion number of the two ground states. Okay? So I just choose 0 for fun. Okay? If I chosen some other value, I would have had to put some subtraction in this fermion number. This is just my definition. What's important is the difference. Okay? I could have put, it's just convenient to do that. Okay? Maybe you want to think of the ground state as being bosonic, if you think of that ground state as 1, 0. This is just arbitrary choice. Nothing really depends on it. Okay? Hey, what would depend on it is that this quantity that I'm computing would be a shifted thing, would be more complicated to write if I chose some other value. This is a convenient choice. Just my definition. Okay. Yeah. 1, 0. Sigma plus is 0, 1, 0, 0. If you just work it out. Okay, that's why it's called sigma plus. It raises. Okay. Other questions, comments? Louder, louder. Super selection rule. What do you mean by that? Sure, one can take linear combinations. One can take A times 1, 0 plus B times 0, 1. In perfectly fine state. In quantum mechanics, there is no restriction to what states you can take superpositions of. No issues. You get super selection sectors when you have something more interesting. When you have infinite number of degrees of freedom and so on. And superselection sectors have to do with what's happening at infinity. But we're very far from that situation. We're in quantum mechanics, 1 degree of freedom. No superselection. Okay, other questions or comments? Excellent. So now I want to quickly explain one thing that we'll come back to in more detail as we go on in the quantum field theory contexts. And the thing that I wanted to point out is that while we did a pretty bad job semi-classically at evaluating the number of ground states, we did a pretty good job semi-classically at evaluating -1 to the power trace of -1 to the power f on the sector of the ground states, on the zero energy subspace. This we evaluated quite effectively, right? Because we got, semi-classically, we computed it as 3 minus 2, which is equal to 1. And quantum mechanically, we also computed it as 1. So we did pretty well for that. And you might wonder, was there a reason? Was there a reason that our semi-classical calculation did so well for computing this slightly strange object? This trace -1 to the power f times trace -1 to the power f on the ground state sector, whereas it did pretty badly for computing the total number of ground states. And so the answer to that question is very interesting. I'm going to take 2 minutes to tell you about that. The answer to that question goes as follows. Look. Let's look at the representations of the algebra. So we had this psi star is equal to 1. Okay? So, sorry. Let's look at our supersymmetry algebra. We have q star is equal to 2 times the Hamiltonian. Okay, so since q and q star commute with h, we can try to find representations of q and q star, eigenvalue by eigenvalue, in the sector of h. Now there are 2 possibilities. All eigenvalues of h are either positive or 0. If h is 0, if E is 0, okay, then the representations of this algebra are simply that q and q star both annihilate that state. It's a one-dimensional representation. On the other hand, if E is non-zero, then this, up to a rescaling, is the same algebra as this. And q and q star, up to a rescaling, are represented by sigma plus and sigma minus. Okay? And since q and q star, you see, this q and q star are represented by this 2-state system, and the 2 different states in the 2-state system, okay, can be under -1 to the power f diagonalized and will have eigenvalues plus and -1. Okay? So what we see is that if you look at the algebra that this is generating, we can look at the states, energy by energy. There is one special energy where representations of this algebra are one-dimensional. And all other energies, representations of the algebra are two-dimensional. And the 2 different states have -1 to the power f plus 1 and -1, and therefore have trace of -1 to the power f is equal to 0. Yes? Yes. Yes. More degeneracy. Hang on for 2 minutes. I'm trying to explain the connection between the semi-classical and the quantum calculus. That's what I'm trying to do. Hang on for 2 minutes, it'll become clearer. There are always 2 states. That's just one state at that end. I mean, there could be many states, but this representation theory, they're in different representations. Exactly. So firstly, we looked at trace of -1 to the power f. So the first comment is that we have looked at rays of -1 to the power f only restricted to the ground state sector. This is what we looked at. But that is the same thing as trace of -1 to the power f on the whole Hilbert space. Because any state that's non-zero energy pairs appear in pairs that cancel in pairs in the sun. Now, this is a bit slightly inaccurate because you say the Hilbert space is infinite dimension. And when you've got an infinite number, infinite dimension, you have to know, in order to know whether you're getting what you're getting, you have to be able to regulate that infinity. The good way to regulate this infinity is with the e to the power minus beta h. This is good because then it forces the cancellation energy by energy, which is what we know works. Okay? Because only states of zero energy contribute, the answer is independent of beta. Because in the end, h should be set to 0, so the answer is independent of beta. But putting this here gives this quantity meaning. Do you understand? You say, if you have a sequence of an infinite number of ones and an infinite number of minus ones, depending on how you group them, you can get any number. This forces you to group them in the way that makes them cancel for states of equal energy. Is this clear?
There was a constraint.
How do we know that for excited states there may not be only one state? That's the question you're asking? Because of the algebra. This algebra here has no one-dimensional representation. You want to find operators q and q star such that q anti-commutator q star is equal to 1, is equal to some number. Now, if you've got a one-dimensional representation, q is a number, q star is a number, and this will not happen. We also want to find, I should also say that we want to find q squared is equal to 0, q star squared is equal to 0. Of course, you can find anti-commutators equal to 1 by choosing, but you can't then do it. You can't satisfy this whole algebra. Sure, the full Hilbert space is a reducible representation of supersymmetry.
Even the ground state.
Sure, it could be. It could be. Representation theory does not tell us that there's only one ground state. Representation theory would allow arbitrary numbers of ground states. That's what you're saying, right? Each one is in its own representation. The representation theory has not given an argument for the number of ground states being 1. All we have done so far is to note that to compute the number of ground states, this representation theory had nothing to say. We had to do a dynamic calculation. Okay? I'm now trying to explain to you why the semi-classical calculation got the computation of this quantity correct, even though it got the calculation of the number of ground states wrong. Okay? Now look, what we've seen here is that this quantity, okay, was the thing that we got right semi-classically. I want to try to explain to you why, if you make an approximate calculation for this quantity, you will get the right answer. Why will that happen? See, suppose we were in our situation where we had 5 ground states, okay? Such that I'm now writing the eigenvalues under -1 to the power left, 1, -1, 1, -1, 1. Okay? And suppose, you see, what could happen quantum mechanically to this system? What could happen is that some of these eigenstates, some of these states, instead of having 0 energy, as the semi-classical answer suggests, actually have slightly positive energy. But we've seen that representation theory forces states to have slightly positive energies in pairs. So let's say the whole spectrum here included, this is energy, included some pairs of states at some non-zero energy separated from this guy with a gap. Okay, now a small correction, suppose it's going to lift one of the +1 states. It will also have to lift one of the -1 states. Because at the new energy, states occur in pairs. Okay? So what could happen, and what we're seeing does happen in our case, is let's say that two of these guys get lifted where one remains. Suppose that happens, schematically speaking. Okay? Now, this completely changes the number of ground states. Changes it from 5 to 1. But what it doesn't change is trace minus 1 to the power f. Evaluated on the number of ground states. Because the pairs that can lift and go to non-zero energy are precisely those pairs which under trace minus 1 to the power f gives you 0. Okay? So this, one second. So this very sensitive thing of something getting a very small non-perturbative energy that's very hard to control, by some approximate calculation, is something that the calculation of this quantity is blind to. Okay? So this quantity here has a name. It's called the Witten index. I've defined it for this very simple model, but you see, for any theory that has an algebra like this, you can make the same definition. All the arguments were actually abstract and didn't depend on the model in question. And so what we've seen is that we've got a very nice quantity here, namely trace minus 1 to the power f. Okay, trace minus 1 to the power f evaluated on either the ground state sector or on the whole Hilbert space appropriately regulated, which in the supersymmetric theory can be calculated by crude means. You make an approximation, you'll get it right. Okay? There's another quantity that is of great interest often. The number of ground states in your system. Okay? That is much harder to get right, as we've seen in this very special example. You may have to do very non-perturbative physics. Okay? So there's much cruder quantity that contains much less information that's easy to calculate. So Witten index. Okay? And a much more sophisticated quantity that contains more information that's harder to calculate, that's the number of ground states. Now, what fixed points? What do you mean by fixed points? Yes. 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 Okay, now there are many things that are getting conflated here. Firstly, conformal invariance, and you want conformal quantum mechanics. Okay. When we start talking about quantum field theories, okay, we will very carefully, that's much of the plan of these lectures, to explain the representation theory and the phenomenology of the superconformal algebra. Okay? But here we are not, quantum mechanics is not defined by flows away from fixed points. That was what is in your mind. It's defined like Schiff defines it. It's completely well defined. Harmonic oscillator is one of these problems. Okay? Now, your question about conformal quantum, is there supersymmetric conformal quantum mechanics? If that's the question, yes? Wait, again, there are two. I mean, our base space, circle, you mean this X space is on a circle? Yeah, that's not allowed in our problem. Our problem has no translational invariance. It's got a potential. It's not the translational invariant theory. It's like harmonic oscillator. I'm sorry, maybe. Oh.
What happens
if you were to periodically identify X? Okay. If you were to periodically identify X, so you would to deal with potentials that had a periodic symmetry. That's your question. Okay, so suppose I had a potential that has a periodic symmetry. Okay. Once again here, I think this integral here, would probably produce a periodic function. Yeah, periodic potential and cut it off from 0 to 2 pi. Yeah. So, so this state would still be well defined. It would be well defined for each of C1 and C2. It would appear. And so you would get, it would appear that you would always get two states, two ground states. Now, let's check what the Witten index of that thing would be. Okay, so suppose I've got my my 0 to 2 pi. It would go something like this. This is an example of one of these periodic potentials. Okay, some cosine kind of thing. This would cut at 2 points. Witten index would be 0. These two ground states will come with plus minus 1. Okay, okay, good. So, okay, good. So if that question, this is an interesting example. This is an example where you see that the Witten index is 0, but you have two ground states.
This is, in many cases, just the Euler number. I could have just said that the Euler number of the circle is 1.
One could have said that, but we're not so sophisticated. Okay, okay. That's right. That's right. That's right. That's right. Okay. So, but this brings us to a very important point. This brings us to the question of when does the Witten index carry interesting information? See, when the Witten index is non-zero, it ensures that the number of supersymmetric ground states is non-zero. However, when the Witten index is 0, it doesn't tell you anything. Also, when the Witten index is non-zero and has a certain value, it doesn't tell you how many supersymmetric ground states you have. You could have more than that. But it tells you that there's at least one supersymmetric ground state when the Witten index is non-zero. However, Witten index being 0 is a null result. Tells you you may or may not have supersymmetric indices. And in fact, there are many practical situations. Possibly we could, if we thought about a device as more sophisticated index that would show. Yeah, there are practical situations in which you could compute trace of -1 to the power f times some grading quantity. Yeah, suppose there's a flavor symmetry f prime, which commutes with the supersymmetry. Then this is also protected. Okay, and this might be non-zero even if the Witten index was 0. So there may be more sophisticated indices that show you the presence of these states, or there may be no index. Okay, so the Witten index is partial information about the ground state sector of the theory. Okay, it's very useful because it's easy to compute. Okay, but it's not complete information, as you point out, if that was the point of the question.
When we identify this line, we also have the possibility of having even number of.
Yeah. Two was an example. We could have had.
At the classical level, obviously there's no way of thinking the one, but even at the quantum level, I suspect
There will always be two ground states. At the quantum level, this calculation tells us there are always two ground states. Okay? So here, but you see, the quantum level, we will see two ground states, and if we worked hard, we would find that the two ground states have plus minus 1, obviously. Because one is 0, 1, the other is 1, 0. So the Witten index, quantum mechanically 0, classically is also always 0. Because the periodicity forces as many pluses and minuses. So it's consistent. This is an example of the other thing, where, you know, where both the semi-classical answer and the exact answer have non-negative number of supersymmetric ground states. They're different in number, but both have Witten index 0. Is this clear? So this, yes?
If the indexes were taken in the plane case, why did we get one, at least one?
Why did we make Witten index 1? You see, the plane case is a bit subtle because it's not a compact manifold. Okay? Compact manifold is where that thing is precise, because when you go to infinity on the plane, okay, so we have to it's this potential that essentially did things. Okay. See, the point is that the harmonic forms on just exactly the plane would just be, that your calculation would give you would just be constants. It would be not square integrable. You need it. Yeah. Okay, so you have to do it carefully. Okay, yeah. On a circle, we should also consider the case where W is antiperiodic, but this wave function then would be antiperiodic. And then we would have to, wave function would not be antiperiodic. The integral would be what? So let's take an example. It would not be analytic. I mean, that's correct. Okay, let's take an example. Let's take, so antiperiodic. So let's suppose that our thing was minus pi to pi. Our space was minus pi to pi. And let's say minus pi by 2 to pi by 2. And we took sine x. This is our antiperiodic potential. Okay. Now, this thing here, the integral will be like cos x. Okay. Now let's look at cos x from minus pi by 2 to pi by 2. That looks, it starts off at, it goes like this. Yeah, periodic everywhere. Yeah, if you want it to be periodic like everywhere, no, not at two specified points. Okay. Okay. Songman is pointing out that there might be that I might have a situation where I've run into a contradiction, because it might be a situation where I would claim that exactly there were two functions, whereas the semi-classical answer gave us Witten index 1. That's what Songman is pointing out, and there's some issue with this. And his situation is one in which we have ends to our potential. So let's suppose maybe another situation which is sort of nearer to what he wants. If you have exactly a circle that you want for every point x goes to x plus 2 pi is periodic, then this W prime. But let's say that we have boundaries to our potential, and we demand that size. Okay, let's discuss this later. Yeah. I'm sure there's an answer. I don't know what it is. Yeah. If anyone knows the answer, they could. Anyone has a clear suggestion? Near the boundary? That might be. That might be. That might be. That might be. It's an interesting question. Yeah, exactly. It jumps, right? Yeah, that's what I was. Yeah. It looks non-analytic here, is what you're saying. Yeah. Yeah. Yeah, it is there's something sort of funny about that. But okay, I don't know. Okay. Now, how much more time do I have, please? Done. Okay. Maybe it's a good point to stop in.